What actually happens in that split second after you hit send on a prompt? Let's take a look inside. Millions of people use screens just like this one every day. You type a question and a polished answer appears almost instantly. But getting a machine to understand the natural flow of human conversation used to be a struggle for even the fastest computers. Early language models process text sequentially, reading from left to right. Think of it like a game of telephone. The first person takes in a word, builds a tiny summary, and whispers it to the next person in line. As that whisper travels down a long sentence, the information gets distorted. By the time the computer reaches the end of your prompt, the meaning of the opening words has often faded or been forgotten entirely. Because each step relies completely on the one before it, you cannot split the work across different computer chips. The system has to wait for each word to finish before moving to the next, which makes it impossible to train on the massive datasets we use today. To truly ingest the library of human knowledge, engineers had to stop forcing machines to read like we do. The machine needed to look at every word in a sentence all at once. This new method treats language like a highly coordinated assembly line. The first station on this line chops your sentence down into raw materials, called tokens. A token is not always a full word. When the computer encounters a complex word, it breaks it apart into common roots and prefixes. This allows the machine to recognize the same help inside helpful and unhelpful without having to learn each word from scratch. Computers do not understand English, but they are exceptionally good at navigating coordinates. The next station converts your raw token blocks into a massive three-dimensional map, assigning every piece of a word a precise mathematical location. The map is organized by meaning. Words that share similar contexts in human writing are plotted close together. Cat lives in the same geometric neighborhood as kitten because the data shows they are used in similar ways. But the map doesn't just show who neighbors whom, it shows the relationships between them. If the path from man to king represents the idea of royalty, the machine can apply that same path to woman to land on queen. It uses these geometric angles to solve word puzzles through pure math. At this stage, the machine has a hyper-precise coordinate system, where every word has a mathematical address based on its relationship to every other word. Mapping words to numbers is a great start, but context changes everything. Take the sentence, "The trophy didn't fit in the suitcase because it was too big." As humans, we recognize that "ig" refers to the trophy. A machine has to calculate that connection from scratch. This happens in the self-attention station. Here, every word looks at its neighbors to decide which are most relevant to its meaning. Think of it like a highly specific search. The word "it" reaches out to every other word, looking for a match for the trait "big." The words "trophy" and "suitcase" both respond with their own traits, competing for the strongest connection. The machine performs thousands of cross-multiplications to weigh these responses. It isn't following a rule of grammar, it is calculating which relationship is mathematically the most probable. The math reveals that "big" is a property describing the trophy more likely than the suitcase. The word "it" absorbs the value of the trophy, enriching its representation with that specific context. This process happens for every word in your prompt at the same time. The model builds a contextually enriched version of the sentence that understands deep, hidden relationships. After the entire prompt is broken down and cross-referenced, the assembly line performs its final task. It generates a probability distribution to guess the single most likely piece of text to come next. Once it prints that next piece, that new word is fed right back into the start of the line. The machine reads the new, slightly longer sentence, runs the entire process again, and predicts the next word, over and over again. This method allows for speed, but it has a hidden limit. Because every word has to check itself against every other word, doubling your prompt length quadruples the work. Processing a long document requires hundreds of specialized GPUs working together to keep up. Yet this intense cross-referencing allows the model to learn new patterns just from the prompt itself. You can show it a few examples of a new task, and it can simulate the learning process within its own architecture without needing any new training. Every word we see on the screen is the result of this highly coordinated assembly line, a triumph of engineering that uses geometry and probability to chart the shape of human communication. Understanding the assembly line removes the mystery of the black box,
turning AI into a tool we can finally begin to explain. If you found this dive into the machinery of language helpful, hit subscribe, and we'll see you in the next one.